Hello everybody, welcome back to While True Learn. Last time we finished a few levels involving the perceptron, and today let's move on to the next level, RL0, which I assume stands for reinforcement learning. Reinforcement, yeah. Okay, hello, V is a society of peoples who love cats. We want our cats to have all the best. We want the cats to drive cars with no humans inside. But the cats have no hands, cats has paws. Can you make a car that self-drive? Yours, Dr. M.O.W. Cat's human person. Oh, it's a cat writing this. Okay, maybe I should change my voice.
Yes. Please excuse the grammar. We are not cats, we are humans, but we can't type well because we have paws and no hands. Terrible car accident, bad surgery is why we need self-driving cars. Haha.
That was terrible. Recognizing objects. In reinforcement learning tasks, nodes work in a bit different way. All data is initially unspecified and your task is to recognize it and transmit it to RL agent, the AI. Okay, SIFT object detection. Looks like we're working with the SIFT module again, except this time it's recognizing different things that are not just simple shapes. Gets the unrecognized data on the input and classifies them as either an object or as a road. Objects go to the upper socket, roads go to the bottom. In the real world, SIFT, Scale Invariant Feature Transform, is one of the most powerful. Okay, we read this already. Okay, so what's happening here? We have different types of objects, and then we have this module. Do I just pass this in and then RL agent? So I'm guessing we just do this. What happens here is we take the input from the front LiDAR, we pass them into the object detection module, and then when it comes out, it will be classified. And what we're going to do is take the classified object data and pass them into the reinforcement learning module for further processing. So the reinforcement module is basically like a second stage to our AI system right here. Reinforcement learning is actually a very powerful technique. So it does a lot more than just classification. It can basically take any kind of input and any kind of output and learn the relationships between them to be able to predict what output is associated with each input. Okay, complete, cost 75. Okay, tune. Ooh, okay, training model. On this screen, you'll be training and testing your AI. AI acts basing on data you've been recognizing when building your scheme. The data about surroundings on the road are processed from your scheme to machine learning model. Your car won't be capable of learning and detecting obstacles without it. Target average speed. The goal in this type of task is to make the AI clever enough to be able to reach the target average speed level. Supervised learning. Press supervised learning and drive the track yourself using WASD or arrow keys to teach the AI. Be careful, the car sees only objects inside a LiDAR area. Green. Okay, yeah, that's going to be important. Press supervised learning to proceed. Okay, so... Oh, no. Okay, the red one's my car. Okay, so I'm gonna... Every time a car comes into the front of the green detection area, that's when I'm going to change lanes. Because if I just change lanes before that happens, then the AI is not going to know why I'm changing lanes. The AI just thinks I'm driving on an empty road, and I'm just swerving across lanes in different ways. So every time, yeah, see, now the AI can see there's a car, that's when I change lanes. Okay, that seems pretty okay. Car training, press training and watch the car's AI trying to reproduce your actions. We hope you've been driving safely in that supervised learning stage. Press training. Okay, now this is the AI doing things. So it looks like initially without any training the AI doesn't know what to do and it doesn't do anything. But if we evolve... Okay, now the AI is crashing. It's not very good. But yeah, your model has achieved the target speed level. Press test and enjoy your results. If the result isn't good enough, try training the car again. So it looks like the default speed is 50, so even if the car doesn't do anything, it still goes at 50. And then the target is 51, so literally if it makes any progress at all, then it's automatically good enough for this level at least. Can I retrain? Launch complete. Result. Average speed is 57.2. It looks like it was still crashing a few times. Your AI cost, and then server's cost. Can I retrain? Let's do another round of supervised learning. We can tell the car, let's see if we can get the car trained a little better. Okay, so I'm going to keep the top speed at 60. I'm not going to speed up too much. And then whenever I see a car, I'm going to brake and then go to the other lane. Okay, do training again. Yeah, doesn't seem to know what it's doing. Well, it says it achieved the target. I don't really know. This seems like still a pretty bad. Ooh, okay, it's switched. Okay, it's doing a pretty decent job. Yep. It's doing a pretty good job. It crashed there, but it got to 61. That was better than before. Looks like I got more. Let's release. Okay. And then we can go to text recognition. Looks like this is just a regular level with perceptrons or something. We are aware that you were able to create a text recognition system based on the Rosenblatt perceptron. We need a similar system that would also be able to distinguish vowels from consonants. This task is simpler, but more accuracy is required. Okay. Deep news. Rosenblatt perceptron, first perceptron machine neuron, was invented by Frank Rosenblatt in 1957. Frank created Mark I in 1960. Mark I is a perceptron machine that can recognize English letters by their shapes. Okay, triangles go in both. Squares and circles go in the in respective output streams. Okay, how do we do this? The target is just one node. Okay. So I'm thinking this one needs 18, this one needs 30, so about twice as many here. So I'm thinking we can just train it and then put the triangle and squares over here. We have twice as many, and then circles go over here. Let's do some training. And stop when it's optimal. And then we just test. Yeah, I don't really see how we can do it any other way when we're only allowed one node, so that better have worked. Yep. Alright, looks like we got a startup here, self-driving car. Hi, we're trying to launch our self-driving taxi service. It's a very promising startup, but we have a problem. Our algorithm makes a lot of errors when it tries to recognize traffic lights. As a result, the car sometimes moves instead of stopping. We hope you can solve this problem. The code must be working very fast. Join startup. You are about to invest 4,000 in the startup. Oh, okay. Yeah. So I need to make at least 4,000 back to break even. You don't need to train your nodes while working on a startup. They already have the minimum error margin because time is money. Okay, okay, that seems incredibly simple. Okay, it does require 90% accuracy and 85% accuracy, and we don't have that here. We have, 80% error. So if I test this, it's going to probably not hit the accuracy mark over here. I mean, in the long run. as soon as a bad one comes through, it's going to tank the accuracy rating, so it's not going to be good enough. So I have an idea for this. So we are going to do 2 layers of this stuff. Actually, we can put another one here. We have 3 processing in parallel. So we have 3 different shapes, and we're going to feed each of the shapes into one of these modules, and then we are going to reclassify them. So over here, supposedly all the circles are going to be here, but the classification could be wrong. So if it's a circle and then the second layer also confirms it's a circle, we can say it's a circle. But if it's a circle but the second layer says it's a square, then we are kind of screwed, right? I guess we just, I don't know what this is going to be then. We just shuffle it into a random slot maybe? If it's circle and it says it's triangle, then we have no idea. Let's try this. Okay, if it says a square and the second layer detects a circle, we're just gonna shuffle it into random places. I guess we're pretty much assuming the second layer is more right than the first layer, which is not exactly right. But we'll try this, and see how it goes. But the idea is, if we do this, then the error rate, the objects that come out of the wrong outputs, is going to be 20% of this 20%. So it's going to be a 4% error margin. Let's try that. It's going to take it twice as long to process each object, but we're going to get much higher accuracy. In the real world, this isn't necessarily true, and this is still doing terrible in accuracy. In the real world, this isn't quite true, because if you use the same modules to do the classification, then it's prone to make the same kinds of mistakes as well. So if it's a circle and it gets misclassified as a triangle, then even after the second time, it's still likely to get misclassified as a triangle. It's not going to change its mind just because you passed it through 2 layers. And the accuracy is not good. I see, because we have some triangles, but I saw circles coming in from this way, because what happens is most of what we get here are circles, and with a 20% error rate, even 20% of the legitimate circles that we get on this level is still being sent to the triangle. So this is getting a lot of incorrectly detected triangles and incorrectly detected squares from the first 2 layers. Okay, so let's do maybe 3 layers. We're going to do that again. That's going to be really annoying though. Okay, if it passed the circle twice, we're good. We don't need to worry about that. Can I trash? No, I can't trash. That's bad. Okay, yeah, we can do this. Okay, so all the misclassified ones, if it says a circle but a square the second time, it's misclassified, and we're going to put all the misclassified into another layer of the perceptron. Square square is correct, so we're going to pass that to the square. Circle, square are misclassified. Triangle is correctly classified, so we're going to keep that there. And then all the misclassified ones, we're going to pass it through a 3rd layer. So the 3rd layer can have a final say about what shape it thinks it is. The 3rd layer is still going to have a 20% error rate, but it's better than 1 layer because the 20% error rate only applies to ones that were already misclassified by the first 2 layers. Okay, let's test that. The vast majority coming through here should be circles. We shouldn't have anything else. Same thing with squares over here and triangles over here. So we are getting that. And then all of these coming through these lanes are misclassified stuff. Or I guess, misclassified by either the first layer or the second layer. So we have a mixture of those coming in, and then this third layer is going to reclassify them with a 20% error rate, but looks like that is good enough. Oh no, triangles are still not good enough. How could we make that better? Wait, here's a weird idea. What if, can we feed it back to the original input? This is something they didn't teach you, but it looks like you can. You can feed the misclassified one back to the first layer. That way, if they keep getting misclassified, they'll keep looping back, and only the ones that are supposedly correctly classified will go to the output. Let's test that. Okay, now we're getting a jam. So the classification seems okay, but we are getting too many objects jamming up the layer here. So that should be easy to fix. So instead of doing that, we are just going to feed them into a separate perceptron to act as our first layer. And then put the outputs. Okay, let's test that. Yeah, the triangle accuracy is still not super great. As I said, because it has 20% error on each stage, theoretically there's going to be about 4% incorrect triangles coming in. And it looks like that's about it. It looks like the line is, halfway between 90 and 100, so that's about right, about what I would expect. And then the rest is up to the random number generator. Okay, I think I'm going to accept that. Let's release. Yep. Go automatic. Okay, and then here all I do is next day. It's not always possible to satisfy all your customers in one day. Users with unfulfilled requests are shown in red color. You don't have the instruments to solve this problem for the startup, but you'll get some to handle the future ones. Okay, so yeah. Let's keep going. Same users. Okay, I made 562. I invested 4,000, so let's keep an eye on that. The hype is yellow. That seems good. Is that right? No. Green hype is good. Yellow hype is not. Yellow hype means it's starting to die down, if I remember correctly. I'm still getting income though, so let's keep going. Yep, now the hype is gone, and the income is going to start coming down. Yeah, to be honest, I don't really understand how this graph works. I think it's drawing new bars to the right, but then instead of having all the bars move left by one, it's having the same bars morph into the next one. So if I press next day, I think this bar is going to grow up to this level, and then this bar is going to shrink to this level, and then the next bar is going to move to whatever the new day is, which is kind of confusing. I wish they animated this a little bit differently, but I'm just going to keep going. Ooh, we made 2,000. Yeah. We're almost 3,000 up. Okay, just keep going. It's going up and down. We made another 2,000. Yeah, we are way into the realm of profitability. We're still making tons of money. Okay, this is great. Okay, that's starting to go down. Okay, next day I imagine it would get negative. Yeah, I'm wondering if I go one more day, it'll be the end of the week and I'll get paid. I wonder if the amount that we collected early in the week is going to offset the negative later, and then we'll still get paid a positive amount. Let's try that. Yeah, 788. We still get paid a positive amount at the end of the week, and then now it's time to cash out. Awesome, we have 18,000. Okay, let's look at some of the things. We don't have anything particular that we can do right now. We've read all the emails. eBay, we can buy some new stuff. Cactus fade haircut. Brush your haircut with your hand for a perfect hairstyle. Sure. Back propaganda poster. Data scientists of the world unite. Back propaganda is play on words from back propagation, which is a technique used in reinforcement learning and neural networks. Alright, that seems okay. Nodes, yeah, in one of the emails they did mention I can get random forest and other nodes to help with my training, but it looks like I can't do that right now. Hardware, there's nothing new. Cat skins. Viking helmet, let's get that. Cyborg, he needs your clothes, your boots, and catocycle. We have lots of cash, so we can... Ooh, WTLVR increases respect from developers. Okay, I hope the developers respect me more now. Let's look at all our cats. So this is a VR one, this is a cyborg one, this is the Viking, and then, oh, we got a Santa one. Where did the Santa one come from? I guess that's the original, but maybe his chin became much bigger? Is this new? This is new just for December? Because I don't think it looked like that before. Oh, we got some fast food and more coffee. We got this camera here. That's from the end of chapter 1. We got our poster. Does this drawer open? No. I still want to see the raccoon. Yeah. Here you go. Okay. Let's get back to the tree. Okay, let's do one more level. Parallel calculations. Hello, we represent a scientific center. Our current programs are underperforming. Can you parallelize our calculations? To process data, your nodes need computer power a server. Certain nodes require more than one server. The more servers you use, the more expensive your scheme becomes. In the game balancer, this node routes elements to the least overloaded socket. Warning, this node requires additional server power. In the real world, a load balancer is the device that distributes network or application traffic across a cluster of servers. Load balancing improves responsiveness and increases the availability of applications. Okay, so balancer, okay, this is just a tutorial then. It's not really doing anything. We just need a balancer. Okay, from what I see, it used to cost 2 cat bucks per second, but because we're using a balancer here, let me try to delete that. Yeah, it's not using anything right now, but if we put a balancer here, it's going to cost 4. If we put another one, it costs 8. Yeah. It's just a simple tutorial on how balancers work. Test. Yep. Good. Okay, and that'll be the end of the gameplay portion of this episode. Hope you enjoyed. If you want to hear more about reinforcement learning and neural networks, feel free to stick around. Otherwise, you can skip to the next episode. In this episode, we got some hands-on activities using supervised learning and reinforcement learning. Roughly speaking, machine learning techniques can be classified into 3 categories. Supervised learning, where we show the agent exactly what we want it to do, and the agent learns exactly that. Reinforcement learning, where we assign a score to the agent's output and the agent tries to produce outputs that maximize the score. And unsupervised learning, where we only tell the agent what its final goal is and the agent has to figure out how to achieve that all by itself. I actually did a research project on reinforcement learning while in school, so I'm kind of biased toward it. But all of these are currently mainstream techniques with lots of active research going on right now. We also read a bit more about the perceptron, which is a neural network. In Hollywood and maybe in your imagination, a neural network might look like this, but in computer science it actually looks like this. Each node, or so-called neuron, in the neural network is really just a fancy calculator. All it does is add up numbers coming in on its input side, with each number multiplied by some factor, and then sends the sum out on its output side. The exact factors that get multiplied in each case is adjusted by training, and that's what determines the neural network's overall behavior. And that's it for this episode. Hope you enjoyed. See you next time.